Let's do some performance testing. So I've made what's called a naive hash list, which is not a hash list at all. Instead, it implements the HashMap API, but just using just using an array list of entry objects. So let me just show you what it looks like. For put, what I do is loop through all of the data stored so far and check to see if we already have the key stored. And if we do, we update the value and exit. Otherwise, we add it at the end. So as you can see, this should run in big O of n time because we have to loop over everything to see if we already have a key stored. For get, same thing. We have to loop over all the data to search for the key that we want, and then we'll return the value, or if we don't find it, we'll return null. So that's the naive hash list. Let's see how it performs. Here's the code that I'm making available to you. First, I construct the hash list that I have. Next, I have a method that will construct a list of randomly generated strings. So you can specify how many items in the list, and you can specify the length of the string. So right now, I'm going to generate 1,000,000 strings, each of length 4. Then I loop through my list, and system.nanotime returns the current time in nanoseconds. So I record the time, I put in the first key in my list, and then I record the time again. And then T2 minus T1, it measures just the amount of time that this single operation took. And then here I'm dividing it by a factor that will convert nanoseconds into milliseconds. Finally, I take that time that it took and I add it into this aggregation variable where I'm measuring the total elapsed time that it took to do all of the put operations. And then I increase the number I've added because I just added one. And then I do the exact same thing for get. For get, I get a random element out of the list of things that I'm adding. And then I set the time, I try and find the thing in the map, and then I get the time again. And so this is the elapsed time that it took. Sorry, this T1 minus T2 is the time it took to perform the get operation. I convert it to milliseconds, and then I add it into this elapsed variable. So every 10,000 loops, I'm going to print a data point, which is how many things have I added up to this point, and what's the total elapsed time it took to perform the get operation once per loop on those 10,000 things. So here we go, we're running it. And as expected, you can see it's taking longer and longer and longer, and the amount of time it takes is clearly not linear because the slope here isn't constant. I'm sorry, because the slope here isn't, the slope isn't constant. Let's let it do like maybe 2 more. Here, I'll pause it for you. Wow, this is taking a really long time. You can see how long it's taking. Okay, maybe that's enough. All right, so we're not going to go all the way to 1,000,000. What are we at now? We're at 100,000. Here, I'm just going to wait for the one last one. All right, there we go. Okay, I'm going to stop it, and we'll plot this much. So here I am in Desmos. I just copied the, whoops, where are we? I just copied the coordinate pairs here from my console. Paste them here into Desmos. And as you can see, this looks fairly quadratic. Which is sort of what we expected, and I want you to think about why. Let's try one of the actual HashMap implementations. So here I am back at the top. Because these all implement the same API, I really just have to change this to like hash list linear probe, for example. So this is my implementation of a HashMap using linear probing. Let's show the console, and let's run it again. Okay, that's pretty quick. That's all 1,000,000. Let's plot them. Where's my plot? Here it is. All right, here we are. So let's plot it. And there you see it. You might wonder what happened to the other graph. There it is. Wow. I wonder what a good way to scale this is. All right, hold on. I'm going to figure out how to scale this. Okay, here we are. So I've only gone up to 110,000. So keep in mind the blue dots, which are my real hash implementation, go all the way up to 1,000,000. And as you can see, they're growing very slowly. However, the array list one is growing very, very quickly. So you can see what a big deal this is. If we were going to use just array lists to do this searching, it would not be feasible. It would just take too long to do large numbers of retrievals. But for the hash implementation, it's like lightning fast. So what I want you to do is try and do this kind of thing to investigate a little bit how the different things that we had control over in our hash implementations affect the performance. So if you did more than one collision handling strategy, you could compare how does chaining perform relative to linear probing, or how does linear probing perform relative to cuckoo hashing. Some other things that you can control, the max load was a big deal. So linear probing performs very, very differently for higher loads than for lower loads. So my max load was 0.4, but you might try 0.5 and 0.6 to compare the difference. Chaining is a little bit less sensitive to max load, although it is still sensitive. So same thing. For chaining, you could compare max loads ranging from 0.3 up to 0.9 to see what they look like. Some other tests that you could run are to compare the relative time for strings of different length for key. So compare key length 4 versus 25 versus 100. An interesting one would be to plot the total number of collisions that have occurred so far as a function of the number of items that you've inserted or searched for, as a way of kind of measuring like collisions directly. This is going to be a little bit harder because you'll need to change your put or get method to return an int that tells you the number of locations it had to test before it exited, so before either finding the thing or deciding it doesn't exist. But if you do that, then you can use that as your y-coordinate plot rather than time. What I want you to turn in is a Google Doc with a screenshot of your Desmos graphs and a short paragraph explaining what it is that we're seeing. And you got to include all the relevant information. So, like, what was the collision handling strategy? What's the meaning of the x and the y? What your max load factor is? And then the whole point of this is to compare things, so you'll have different plots in different colors, and you should say what the different colors represent, like what testing conditions. Then give me a short paragraph reflecting on what you see, so kind of what are you observing, what conclusions can you draw, like what is it telling you about the performance of your hash. Any features of the graph that seem peculiar or you don't have a good way to explain are nice things to note. And then we'll share these and maybe discuss a little bit about them on Monday.